We talked about local extrema. Now let's talk about absolute extrema. An absolute max or min only occurs on a closed and bound region. So when we're looking at local, we're not including any of the points along these circles. It's an open disk. But when we're talking about absolute, it needs to be a closed disk, which means we have to be able to compare all of the points on the disk to what we're claiming to be the absolute max. So here's an example where we have a function and we want to find the absolute extrema, which means we need to not only find critical points, but we also have to test all along the boundary of our region. So we'll start by finding the regular critical points. For that, we're going to need the partial with respect to x, the partial with respect to y. Set them each equal to 0 and solve. These are both pretty simple equations, so we can solve them right away. X should be equal to 1, y should be equal to 2. So we have a critical point at 1, 2. And that critical point, we're not going to bother testing it using the second derivative test because it has to be able to outcompete all of the values along the boundary. Now, taking a look at the picture of the function, I have it graphed here and I've also truncated the surface along the boundary. So this magenta triangle is the triangular region that defines our boundary. And then the surface does not exist beyond that because I'm containing it within the boundary. So we found a critical point which most probably corresponds to the top of this upside down paraboloid. So this is most likely the point that we found at 1, 2, and then the z value would be f at 1, 2. But now we need to check all of the function values along this edge of the boundary. We need to check all of the function values along the back edge of the boundary. And then it's truncated here so you can't see it, but we would need to imagine all of the values along this magenta line plugged into our function. So those are going to be way below what this picture can show us. So if we're looking for all of the extrema, visually, I think we can feel pretty confident that we found the max with our true critical point, but now we need to check to find what the minimum is. And to do that, we're basically going to substitute each one of these boundaries into our function and then apply the first derivative test from Calc 1 to each. So let's take a look along x equals 0. Well, along x equals 0, our function actually just becomes a function of y. It looks like 2 plus 4y minus y squared, because all of the x's go to 0. Along this, we can find the derivative to see that it's 4 minus 2y. Set that equal to 0 to find the critical point, that y needs to be 2. And at y equals 2, we plug that back into our function. So we know that we're looking at x equals 0, y equals 2, and then we're going to calculate our function at 0, 2. And technically, we're going to compare it to the critical point that we suspect is our match. So we're going to compare that to this point that we think our maximum is. So f at 0, 2, we would see 0, 2, and then 2 plus 4 times 2, so 2 plus 8, that's 10, minus 4, that would be 6. So we're comparing this 6 to the value that comes out of our function when we plug in 1, 2. So at f at 1, 2 would be, that would be equal to 7. So we can see that the true critical point did give us a maximum that was larger than the potential maximum we found along the x equals 0 boundary. So we can rule this out as a max. But we do need to check the other boundaries. So let's look along y equals 0. Well, along y equals 0, our function becomes a function of only x, which looks like 2 plus 2x minus x squared. Take the derivative with respect to x. We find 2 minus 2x, which tells us that x needs to be equal to 1. So now we're going to check this point. X equals 1, y equals 0, f at 1, 0. So we're looking at 1, 0. F at 1, 0 would become 3. So we have 2 plus 2 minus 1, so 3. And we can see that this is definitely not a contender for a maximum either. So if we're comparing the three values of our function so far, we have 7, 6, and 3. So far the critical point is winning for the maximum, and this point with the function value of 3 is winning for a potential minimum out of all three of the points we've investigated. But we do have one more to look at, so let's continue on. Let's look along y equals 9 minus x. Now, plugging this into our function, we're keeping x as x, y is being replaced with 9 minus x. Essentially, we're creating a function of only x again, and that function will look like 2 plus 2x plus 4 times 9 minus x squared minus 9 minus x squared. And so from here, we're going to take the derivative again. You can choose to multiply this out, then take the derivative, or take the derivative first, however you'd like. Go ahead and find the derivative of this function with respect to x. Once we have that derivative, we can set it equal to 0 and see that x needs to be equal to positive 4. So we're looking at the point where x is equal to 4, y is 9 minus 4, so y would be 5, and then we need to plug that into our function. If we plug 4 and 5 into our function for x and y respectively, then we find that the corresponding point is negative 11. And if we compare that to the other function values that we found in this process, we can see that negative 11 is smaller than 3, so 3 is not the minimum, smaller than 6, smaller than 7. It's smaller than all of the other values we found, so negative 11 must be the minimum. Absolute extrema is quite a bit more difficult to calculate than the local extrema because we have to test along the boundaries, but great news! In the next section, we're going to find out how to do this more efficiently. There are some application problems in the chapter. I highly recommend that you try those. Feel free to reach out and ask for help if any of them feel cumbersome. But I'm just going to show you the gist of it, and then we're going to move on to show you the quick and dirty way to find absolute extrema.